The final example of dress states I'd like to look at is that of electromagnetically induced transparency. So you can make a simple model for this phenomenon with just a three-level atom. So if you have a transition in an atom between two levels, then you also have a third level. This is often called a lambda configuration because you've got transitions like that and transitions like that, and that's the sort of Greek letter lambda. So if you have a gas of particles like this, and all the particles tend to be in this ground state here, then if you shine light through at this frequency here, then that light is likely to be absorbed and rescattered by those atoms. And then those atoms are going to obviously be opaque to that light. So you try and shine light through, it just won't get through. So it's opaque. But then if you take a different frequency of light and you shine it on resonantly on this transition, even though there are actually no atoms in that ground state and no atoms in that excited state, it turns out that that gas will become transparent. Suddenly that original light will start going through. The reason for that, again, is very easy to understand. If you think about the dress states, we already talked about what happens if you shine light on two states resonantly. In the presence of that green frequency, this state at the top is no longer going to be a good eigenstate. A much better description of the eigenstate of that system, when that purple line is very weak, is actually going to be a pair of dress states, which are going to have different energies split in either direction from the original energy. And that purple line is going to be addressing a space in between the two of them. And so it's going to be off resonant. It's no longer going to be resonant with that. And secondly, it might have some kind of interference between the two. And that's exactly what happens, and that's why the light suddenly starts getting through. Now notice that the distance between those two dress states is going to depend on how strong that coherent field is. And so if we have a graph of the absorption versus the probe frequency, then we'd expect there to be two peaks, and indeed there's a full destructive interference in between, and the distance between those peaks is going to depend on how strong that strong coherent field is. The Rabi frequency of that transition between two things that are not actually populated defines exactly how far apart those dress states are, and therefore they define how far apart these absorption peaks are. Now if we only had a two-level atom, or conversely if we didn't have that strong coherent field, then our absorption might look something like that. Now if we have absorption like that, then we're also going to get dispersion. In other words, we're going to get a different phase shift for the scattered field depending on which side the absorption peak it comes from. So the dispersion is going to look something like this for the two-level system. Now when we've got two absorption peaks, we've got this dress state, dispersion has to have the same limits in the high and low frequency limits, but it also has to cross the zero, it has to have a phase shift across each of those absorption peaks. And so therefore in the lambda configuration, it has to look something like this. And to match them up, it's symmetric obviously, we get something like that. So we get this sharp feature. Now how sharp is that feature? Well, it's got to fit between those two absorption peaks, so it depends on the strength of that strong coherent field. When that coherent field is very strong and the splitting is very large, then obviously that feature doesn't have to be particularly sharp. But as we turn down that strong coherent field, we still get that beautiful absorption interference in between the two peaks, but that dispersion curve is getting all squished up. And so what we're going to get is going to get a very large gradient in phase shift as a function of frequency. And that gradient in the dispersion curve is what affects the speed of a pulse of light. So the reason pulses of light travel at different speeds in materials is due to the slope of that dispersion curve there. And what that means is as we turn down that strong coherent field, we're going to get our pulse of light going slower and slower through that material. So it becomes transparent when we have that coherent field on. It becomes transparent through a narrower and narrower window in frequency, but it also travels slower and slower. And so we have a phenomenon called slow light. So the most interesting thing about the slow light you get in electromagnetically induced transparency is just how slow it can get. You can get light that travels as slow as you like. You can get it all the way down to walking speed if you wish. You can go from 3 by 10 to the 8 meters per second down to 10 meters per second. And all you do is you turn down that strong coherent field. And the smaller that field is, the narrower that window. Of course, in order to actually see slow light, you have to make sure that you have your pulse fit exactly into that frequency window, but you can do that with care, again with lasers. This was first done by Lena Howe in 1999. And that wasn't actually her best trick. Her best trick was where she turned that strong coherent field off entirely. If you let the pulse of light come into your material while you have some finite window where it can get in, where it's transparent, then it takes quite a lot of time to travel across your cell of gas. So your gas might be a few centimeters long, and if you can get your speed so far down that it can spend a significant amount of time actually inside that cell, then you have time to switch off your laser, your control laser, while that pulse is in the cell. And if you do that, that dispersion relation is going to collapse, and you'd expect that in that limit, that light would actually stop. And that's effectively what happens. For that while, you do not have the light, it's gone. But then, when you turn that strong coherent field back on again, out came the light. It was a little bit like having a railway train blaze into a tunnel the size of a thimble, stay there for minutes, and then suddenly blaze out the other side. In those initial experiments, the storage times were actually milliseconds, which doesn't sound like a lot of time, but when you think about how far a pulse of light normally goes in that time, that's a very long storage time. This kind of raises several questions, though. In the limit that strong coherent field is gone, then surely this whole picture about dispersion curves and so forth doesn't really make any sense. And where's the light gone? If the light is absorbed, how can it be just stopped there? Surely if you had light in a cell like that, it would scatter if you didn't have any reason for it not to scatter. What's going on in that situation? Well, it turns out it's vastly easy to understand if you think about the dress states. And once again, the dress states are the actual eigenstates of the system. And because we have a strong coupling between this probe field and our atoms, the actual dress states in this case are called polaritons, superpositions of atoms and light. The particular polariton we're interested in is a superposition of our electric field operator and the coherence operator between the two ground states in our atoms here. So if we label these B and C, and that higher one is A, then our ground states B and C have a coherence between them, and so there's an operator sigma BC. And if we coarse grain that to have lots of different atoms all averaged up, then we have a sort of collective transition operator like that. And we can write what is effectively an annihilation operator for our polariton as a superposition of annihilation operators for our optical field and this collective atomic operator. Where this coupling strength little g is the coupling between our weak field and our atoms, and this omega is the Rabi frequency of our coherent field. And so you can see that as we change the strength of our Rabi frequency for that coherent field, we can change this polariton from being largely optical to largely atomic. And because these are eigenstates of the system, if we initially start in one of these polaritons, we're going to stay in it. And what happens if we change our parameter slowly? So if we change our coherent control slowly enough, then we can follow the adiabatic theorem, and we can say if we start off in a polariton, then we'll stay in that polariton even as that polariton changes character. And that's a good model for what's happening in EIT when we stop light. So in comes light, and when it's light and it's not inside our actual coupled system, then it's purely optical. As it comes into our coupled system, we end up expanding that optical state into a superposition of different polaritons. And then we have something that is both optical and atomic. And because it's got a significant atomic parameter, it turns out that the evolution of this is much slower than the speed of light, down to much, much slower than the speed of light. And then we can change slowly this Rabi frequency. And as we change that Rabi frequency, we get more and more of our state, more and more of our polariton is in that atomic state. And then it gets slower, and we can in fact go to the limit where we are entirely atomic. And so where the light's gone is it's gone into this coherence between the atoms. And then the magic is we can undo it and we can turn our coherent field back on again, and we'll slowly get more light to the point where we end up with our light exiting the other end of the sample. What this polariton picture is showing us is that it's actually the full quantum state of the system that's being preserved up to a global phase. Although we start off entirely optical and we go fully atomic and come back again, you can see that it's actually always the same eigenstate that's going through. And so in fact the quantum statistics are going to be preserved, and we have a full quantum memory here. A quantum memory is where you can take some quantum state, fully store it, and then fully retrieve it. And this is an extremely active and exciting area for experimental physics right now, because there are lots of uses for quantum memories in quantum information processing and quantum computing and so forth.